All right. Let's get started. All right, so let's talk a little bit about the schedule coming up for the next probably couple weeks. I'm going to not be here. Well, we'll see if my flights work out. Last time they sort of didn't, and you all had to deal with my evil twin. So I'm supposed to not be here on October 10th, on Tuesday. So I'm going to cancel class on Tuesday. Because of that, I want to try and get you all doing concrete mix designs as soon as possible. My plan for the lab is as follows, and I'm still tweaking it and toying with how exactly I want to do it, but ultimately what I'd like to do is this. So for the first, and I'll call them the first 3 substantive labs in the class, you all were computing and determining various key properties associated with coarse and fine aggregates. Absorptions, specific gravities, stuff like that. What I want to do is this. I'm going to show you all how to proportion a mix design for concrete. Oh, didn't turn my phone off. Sorry. I'm going to show you all how to proportion a mix design for concrete. And what I'm thinking is, I'm actually going, and we'll see how the data works out, but I'm thinking of actually having you all use the data that you collected in the lab to design a mix and then go mix it, and we'll see the results. So I'm thinking of actually leaning on and having you all rely on the data that you collected in the lab. Now, we might have to tweak some things a little bit here and there to see, we'll see how things work, but that's sort of my plan. Okay, so let me talk about scheduling. So today, if you recall, we had started to talk about Portland cement, and then we kind of stopped because we had labs and the exam come up. So I want to continue that discussion, talk about admixtures, and then get into concrete, Portland cement concrete. Now today, we're going to be busting mortar cubes in the lab. That'll be pretty straightforward. You all cast the cubes. We're just going to test them. Depending on time, I know I want to test at least 1 from each group, and depending on how the results are, we might test 2 from each group. We're probably not going to test all 3 from each group. So we're only going to do a 7-day test for the cubes. We could do more, but we're going to be busting cylinders all semesters, for the rest of the semester. So, you know, once you've seen it once, it'll be fine. Okay. For the 3rd and the 5th, I want to show you all procedures for how to proportion Portland cement concrete, and then we're going to have a full-blown example on the 5th. In lab on the 5th, okay, and this is going to be kind of important. In lab on the 5th, myself, Patrick, I might, get a couple of you all to sort of volunteer to, pick some things up with me throughout the lab. But we're going to demo how to do the full gamut of tests associated with the Portland cement mix. And this is where you really want to, you want to pay attention, take notes. I'll have the handouts for the labs posted in advance, so you definitely want to read those beforehand. I mean, once you begin the mix, the clock starts, and there's a lot of things that we have to assess. We have to assess air content, we have to assess slump, temperature, we have multiple specimens that we have to cast, so you really kind of need to make sure that you know what you're doing. So we're going to do a demo for you so that you all see what happens, and then our first mix design, you all are going to do it yourselves. Now, in terms of homework assignments, I'm probably going to give you your 4th homework assignment on Tuesday. That will involve concrete, and you'll probably turn in the data sheet from this lab, from Lab 5. I told you all that you might have some homework assignments associated with the labs that you turn in together. Well, that's going to be homework 5. Homework 5 is that's going to be the homework that you work on throughout the semester. And instead of each one of you turning it in, I'm only going to get 6 submissions, 1 for each group. So you all are going to work together to produce a lab report. Now, I'm not going to lie, it's going to be a pretty comprehensive lab report, but the trade-off is that you're working on it together and you get to work on it throughout the semester. You won't turn this in until after we bust 28-day specimens for mix design 2. So this is just something to work on throughout the semester. I mean, this probably won't be due until November, December, so don't wait until the day before. So work on that periodically throughout the semester. Everybody okay on the schedule? Yes. Oh, right here. That's a mistake. We'll add 0.2. We'll add 0.2 because I canceled the day before, so that at least had to make you a little happy. There we go. Okay. So 0.2. We'll add 0.2 to the mistake counter. All right. I am still working on grading your exams. My goal is to get that back to you on Tuesday. Okay. So sound good? All right. So I want to finish our discussion on Portland cement and admixtures, and then hopefully, like I said, I want to get you all designing concrete mixes as soon as possible. So let's go ahead and get back into that. All right. Now I'll go back a little bit just to sort of recap, because I know it's been a while since we talked about a lot of this. So I'll sort of start back at the beginning, but I'm going to go real quick because we've already talked about a lot of this. So the first thing that we wanted to talk about in regards, because I mean one of the big topics of this entire class is being able to appropriately proportion and design a mix of concrete. So you could argue that the first half, if not even more than half of the semester, is all really geared towards that one fundamental task. I mean, we are civil engineers. Concrete is a material that we will use throughout our careers. So being able to proportion a concrete mix is very important. I mean, all the stuff that we did with aggregates, I mean, in the end, we talked about aggregates, but a lot of our focus was on determining some very key properties, specific gravities, absorptions, fineness modulus, things like that, moisture contents. All of those values are going to ultimately be used to proportion and design a concrete mix. Okay, so we've learned about aggregates. We're getting ready to learn about cement. I figure you all at least know what water is. 2 hydrogen atoms, 1 oxygen atom. That was a joke, not a very funny one. But honestly, between aggregates, cement, and water, and admixtures, what we're going to talk about, that's concrete. So hopefully you kind of see this is all ultimately going towards that goal. That's where we're headed. So to talk a little bit about cement, I sort of introduced what that concept was. It's a component in concrete. I'm not going to go into this in really significant detail. One thing, a couple things, there are multiple different types of cement. One value that you'll want to remember, and you will see here in a second in my proportion handout that I'm going to give out, that the specific gravity of cement, regardless of what type of cement you're looking at, is always 3.15. That is a constant for cement. It's like, what is the specific gravity of water? 1, right? What is specific gravity? Specific gravity is a ratio of how heavier something is in comparison to water. So something has a specific gravity of 2, it is twice as heavy as water. So the specific gravity of water is 1. So that was a pop quiz, and everybody said, don't bring up water. I know things. All right. I talked about the production of cement, and I showed you all a video on that. I'm not going to get into all that or the chemistry and the production process. I've already talked about all this. I'm going to skip a lot of that. I'm going to skip, properties, fineness. Obviously, you all know that hydration is the main chemical reaction we're interested in. I'm going to skip that. I mean, we already talked about all this. We did talk about voids within cement, right? I think that's kind of where we stopped. The idea that when you hydrate cement, I mean, there is a chemical reaction, and there's going to be attraction between cement particles, aggregate particles, and water. And because of that, you do generate some air voids within a cementitious mixture. Some of them are desirable, some of them are not. And we're going to talk about how we can achieve desirable properties or desirable air entrainment, and how we can avoid undesirable entrapped in air later. So I'm going to skip a little bit of that. I think this is where we stopped as we were talking about properties of hydrated cement. while we might not have discussed them in lecture, you all already know what I'm talking about just looking at this, okay? For instance, one of the main properties that we're interested in terms of hydrated cement is its setting and hardening time. And you already know how to do that, or how to determine setting and hardening time, and that's by performing a VICAP penetration test. And you all did that in the lab. When we were in the lab, our main purpose in the lab was to try and determine how much time was required for the VICAP needle to penetrate to a depth of 25 millimeters, okay? And that basically gives us a rough estimate of a hydrated cementitious mixture's initial set time. So its setting refers to a stiffening or a change to essentially to a somewhat solid state. So that's how much time we have to finish surfaces and get the concrete to its solidified state. That's about how much time we have to work with it. The final set time on the VICAP will be how much time it takes for it to penetrate 0 millimeters, not penetrate at all. And that's once it's completely hardened and there is no working with it whatsoever. Okay. There are some other properties of hydrated cement that are of interest. I have here that we were going to determine or do this demonstration in the lab. I don't think we're going to do that. This is a little bit of a tricky experiment. This is looking at soundness. And soundness is basically the ability of a cementitious mixture to retain its volume after setting. So the long and short of it is you cast a sample and then you subject it to high temperature and pressure and record the change in volume. It's a little tricky, and I think we're going to avoid doing that in the lab, but I just wanted to give you kind of a general idea of how that works. Now, we are going to do this. This should be very familiar. We can look at the compressive strength of a given cementitious mixture. Now, what we've done so far in the lab is to look at the compressive strength of mortar mixtures. Remember, what is the difference between mortar and concrete? There's one thing we don't put in there, and that is gravel, right? Coarse aggregate. Remember, mortar had cement, sand, and water in it. Yeah. So that's something to keep in mind in terms of terminology. Okay. That might show up on a celebration one day. Okay. Now, we are going to perform 7-day testing of some of the compressive strength or some of the mortar cubes today. So it's just something to keep in mind. Hopefully, you've got your data sheets from last week. If not, there's not really a lot of data to record, so you could at least find, if you left it at your apartment or something, no big deal. Just, take a quick note of it and transcribe that later. All right, everybody good so far? Okay. By and large, one of the most important properties, one of the most critical parameters of a given concrete mix is the ratio between how much water you put in a mix and how much cement or how much cementitious materials. And by and large, it's the one property that affects just about everything else associated with a concrete mix design. What you'll find is that when we perform a mix design, and I'll just kind of give you the overall, hey, here it is of our philosophy with mix design. This is essentially how it works. What we're going to do is we're going to take 3 key pieces of information to proportion a mix. We're going to take our required compressive strength, how much compressive strength we want out of a given concrete mix. We're going to take its intended use. So for instance, a concrete mix design for, let's say, bridge pier in Miami that's going to be subjected to seawater and a lot of salt content is going to have a different mix proportion than, let's say, an internal floor slab in a building that's not going to be subjected to any deleterious environmental impacts. That concrete mix is going to be different than the previous. So we're going to take its its target compressive strength. We're going to take its intended use, and we're going to take data associated with the ingredients, what's the specific gravity of the coarse aggregate and fine aggregate and so on and so forth. We're going to take those 3 pieces of information to start proportioning the mix. One of the first things we're going to determine is the target water-cement ratio, because it governs just about everything that we want desirable associated with a mix. And it's one of those trade-off quantities that where you've got to really find a healthy balance. Typically, your water-cement ratio for Portland cement concrete is somewhere between 40% and 70%, and it just depends on your intended use. Now, you got to have water present for the reaction, obviously. So there is at least some minimum amount of water that you need. Introducing more and more water has sort of a trade-off. You do need some amount of water present, not just for the chemical reaction, but for workability. And one of the ways that we'll measure workability in the lab, and you can do this in the field, is to do what's called a slump test. How many of you have ever heard of a slump test before? Okay, so a lot of you have heard of a slump test. We're going to do a slump test in the lab if you haven't heard of it. Now, the long and short of it is a slump test gives you at least some numerical measure of workability. The larger your slump, the higher the perceived workability of your mix is. And throwing more water into the mix will increase workability. But the problem is that if you start throwing more water into the mix, you will decrease your strength. So there is a trade-off, okay? And that's going to be one of the very first values that we select when we start getting into design is what's our water-cement ratio. Here we're looking at these two plots. What we're looking at is essentially a measure of compressive strength as a function of water-cement ratio. And you can see as the water-cement ratio goes up, your compressive strength goes down. And it can go down quite a bit. I mean, we're going from something like 6,500 psi, or let's say on this non-air entrained concrete, 6,500 psi all the way down to below 3,000 psi. And that's one heck of a shift. So, maintaining an appropriate water-cement ratio is very important. One of the last things that we'll do in a mix design is we'll actually correct for moisture within a given mix. Based on an aggregate's present moisture state, we might need to throw in more water, or maybe at the very beginning we were putting too much in and we can actually take some out. That'll make a little more sense when we actually get into concrete mix design. Now, in terms of actually what Portland cement you use, ASTM C150 lists 5 types of Portland cement. This is something you might want to put a star on, nudge, nudge, wink, wink, might show up on a celebration of learning run day. Oh, now we got everybody's attention. I know things. By and large, type 1 cement is the most common cement that you'll see produced in the United States. I'd say probably around 90% of all the cement that we see in the United States is either type 1 or type 2. That's the type of cement that we're going to be using for our mixed proportions in the lab. Type 3 is becoming a little more common and a little more cheaper. Type 3 will give you a high early strength. It's one of those things where you get a high early strength, so there's a little bit of advantage, but it might also be a little more expensive. That's where engineering judgment and trade-offs and whatnot come into play. Type 4 is if you've got really, really massive placements. So if you're casting really, really large elements of concrete and you need to control the heat of hydration, that would be where type 4 would go. Type 5 has high sulfate resistance, so that'd be really appropriate if you're doing something like a bridge deck or something like that, and you're going to see a lot of de-icing salts or sulfates or things like that. Okay, there are other types of cement. I am not going to sit here and go through every one of them. Just know that there are different types for different applications: moderate sulfate resistance, high sulfate resistance, moderate heat of hydration, and the drill. I'm not going to go through every one. You can research that at your leisure. Mixing water, like I said, 2 hydrogen atoms, 1 oxygen atom. That's basically the long and short of it. But I'm being facetious, but there are a couple more things that are worth mentioning. I mean, any really potable water, have you ever heard the term potable water? Potable water essentially is trying to reference anything that could theoretically be drinkable water can be used. You can use non-potable water if you've assessed the impurities and see if it meets appropriate tolerances. You can use seawater for plain, just like regular concrete, but not for anything reinforced. Anything that's going to be subjected to significant loads. Excuse me. What else? Wastewater from mixed plants. That just something to keep in mind. That's actually treated as a somewhat hazardous substance, and the reason why is because of the concrete mixing process. Wastewater from concrete mixing is very basic. Okay, everybody. I'm starting to throw out chemistry terms, and everybody's going, "Oh no chemistry." No, but if you remember, anything that's basic is going to be something that has a high pH. Everybody know what I'm talking about there? Okay, all right. So wastewater from ready mixed plants has a high pH, and that can be a little bit of a problem. There are also practices that are prevented or limited by the EPA regarding wash water, dumping at the job site, dumping at a landfill. You can use reuse water for mixing new concrete, but it's just something to keep in mind. We got to be environmentally friendly, right? Captain Planet. My goodness. Don't know who I'm talking about, right? Okay. All right. Goodness. All right. Okay. Let's talk about admixtures. We've already dealt with admixtures already in the lab. Remember the admixture that we've already used? Remember that? What did we use in the lab for the mortar cube for the VICAP penetration? What did we use? We used an accelerator, all right? And what did the accelerator do? Like, what was its purpose? It made it cure faster, okay? So an accelerator, that particular admixture had a particular purpose, okay? So what we're going to do is talk about various admixtures here, what their purpose is, what they're going to be used for, what they're not going to be used for. I'm just curious. We'll just throw some questions. If an accelerator makes it cure faster, what do you think this does? Makes it cure slower. Okay, so each one has a particular purpose. We're going to go through each one of these. Okay, so let's start off with air entrainers. Okay, now if you recall, I mentioned that one of the ingredients that can go in a Portland cement concrete is air. Okay, now some air content is great, some isn't. Okay, one of the so we sort of split that up into two categories. Okay, so entrapped air is completely undesirable. We do not want entrapped air in a concrete. And what I mean by entrapped air is that comes from not handling a concrete mix properly, it not getting set properly. If you're pouring a slab, it not getting vibrated properly, and you have large unintended voids in a given concrete placement. That's undesirable. We do not want that. Okay. So if you ever hear me use the term entrapped air, that is undesirable. Okay. Entrained air, that is desirable. Okay. Because of the nature of concrete, especially let's talk about concrete in, let's say, exterior applications, applications outside. Let's talk about concrete, let's say, used for a bridge, let's say in West Virginia. Okay. You know as well as I do that in the summer, it can get what? We can see 90s, maybe even triple degree weather every now and then, right? Okay, what about the winter? Okay, we can see 10s, single digits, every now and then below zero, right? So throughout the year, a given exterior application of concrete is going to see one heck of a thermal shift, right? Now, you folks who had me for deformables, even if you didn't have me for deformables, I think you'd recognize this. When things heat up, they tend to expand, and when things cool down, they tend to contract. That's just physics, okay? So having some controlled amount of entrained air in a given concrete application is actually a good thing. They can sort of provide a little bit of a buffer for that internal freeze, thaw, expansion, and can control that behavior and even prevent cracking a little bit. This is sort of a zoomed in, sliced view of a given application. You see these little blue bubbles. Those blue bubbles are representing air that's present inside a given mix. Typically, from a volume standpoint, if we're going to use air entrainers, we like to have somewhere between maybe 1 and 8% of air entrained for a given concrete mix, and that's by volume. It's obviously not by weight, because how are we going to weigh the air inside? So we're going to measure that by volume. Okay. So if we have an exterior application, let's say a bridge deck, a bridge pier, something like that, the use of air entrainers is going to be almost a given. If it's an interior application where temperatures are readily controlled, we're probably not going to use air entrainers. Does that make sense? Everybody okay with that? All right. Okay. Let's talk about water reducers. Okay. Like I said, throwing water throwing more and more water into a Portland cement concrete mix will make the mix more workable. Okay. The problem is it will decrease the strength. So the question is there such a thing as an admixture that will increase the workability without increasing the water content? And the answer is yes. They're called water reducers. All right. How many of you have ever done any or been around any type of concrete work and ever heard the term Super P or super plasticizer? That's what super plasticizer is. It's a water reducer. Okay. Water reducers, they come in various ranges. So for instance, this is looking at a slump test that we will do in the lab. So this might be what the end of a slump test looks like after no reducer. For those of you that don't know how a slump test is performed, it's pretty basic. So there's a flat surface and there's a very standardized metal cone that you set on that surface. You fill it with concrete in various lift, rod 25 times. You all have already had experience with rodding samples because we did that with the mortar cubes. Rod it, so many times, level it off, and then when you lift it, you don't twist, you don't do that, you lift straight up, okay? And lift it, at a somewhat controlled rate. What's going to happen is, the concrete is going to want to maintain that form, but it can't maintain it perfectly, so it's going to fall a little bit. It's going to slump, okay? The more it slumps, the more workable it is. So this might be the result of something, or of a concrete mix with no reducer. This is one with a conventional reducer, and this is, I really like this image because it gives you a perfect idea of how slump is measured. So once you remove the cone, concrete slumps. The easiest way to actually measure that slump is to take the cone, turn it upside down, set it down right next to it, and you can see this metal bar. That's the rod that was used to rod it 25 times. You lay that flat, and then you can use a tape measure to just, from the center of that cone, just measure how far it goes down. We typically measure to the 1/4 inch. So you can see there's what a conventional reducer would look like. There's what mid-range would look like. And if you've ever seen concrete with Super P in it, just goes all over the place. We actually measure that with a flow test that we'll talk about later. Specifically, and I'm not going to get too nuts into chemistry, but if you want to know how a water reducer works, there is a chemical reaction and attraction taking place within a cementitious mixture between cement and water, and they're attracting, and that's where the reaction's taking place. So what a water reducer is doing is it's essentially disrupting the charge between those two particles, and it's disrupting that reaction. So it's keeping everything separate, and it's deflocculating the particles, allowing the concrete to remain a little more workable. Now, the nice thing about water reducers and super plasticizers and things like that is they do improve workability, and again, without increasing water, okay? And they can also increase the strength. The only thing that can be a little iffy is they do allow the concrete mix to remain workable, but once they wear off, the concrete will set, and it will set quick. So it's something, if you're going to use it, that's fine. You just got to be aware of that. We are actually going to have some water reducer in our mix number 2. Okay, so we're not doing that in mix number 1. I want you all to essentially use regular old concrete for mix number 1, and the mix number 2 will spiffy it up a little bit. We'll use some self-consolidating concrete. So it's going to have some different cementitious materials, some water reducer, and some stuff like that. So just to give you kind of an idea. Okay. So on super plasticizer, it can really increase your slump. You can also, because you're getting that same workability, you can even decrease the water content a little bit. Now, it usually lasts somewhere between half an hour, something like that. then it will set, and it will set quick. So it's just something to be made aware of. Okay, accelerators and retarders. So accelerators do exactly what you would think. They speed up curing. Now you might be thinking to yourself, why in the heck would you want to speed that up? Wouldn't you want more time to work with concrete? Well, it depends on your application. If you've got some hydraulic pressure situation, you've got a leak and you need to plug that leak fast, an accelerator might be an advantageous component. Retarders, now retarders are going to do the exact opposite. Retarders are going to delay the initial set time, and there's a lot of relevant reasons why you'd want to use them. I mean, maybe the distance from the concrete mix plant to where you're placing the concrete, maybe that's a long haul. And once that's mixing in the truck, I mean, you all have probably been down the road and seen a concrete truck, spinning and mixing. Well, there's only so much time. They got to get to the job site before that sets. So maybe, I don't know, maybe you got to slow that set time a little bit. Now, if you use a retarder, that's great. You need to make sure you're aware of a couple things. It might reduce your early strength. So depending upon your application, that might be a no-no. It's just something to think about. Everybody good so far? Any questions? Okay. Hydration control. Hydration control admixtures tend to be used more when it's almost like maybe something goes wrong at the job site, or maybe not even something goes wrong, but maybe you're working on a given concrete placement, and then you have to stop for a little bit and do something else before you start back up again. So it's useful in extending the use of a given type of concrete when you've got to place that at a different time. So there's usually a stabilizer that gets put into the mix, and that sort of stops the hydration reaction for a little bit, and then you activate it back up again. So I personally haven't dealt with any projects where that's been used, but it's just something to think about. Okay. Again, there are a whole host of different admixtures for all sorts of different applications, trying to improve permeability, insecticide admixtures and fungicide admixtures, which would be really important if you were casting floors, let's say in a hospital, to try and control germs and whatnot in a given application. Coloring agents, grouting agents. I'm not going to go through every single one of them. You all can again research that at your leisure. Lastly, I do want to talk about some supplementary cementitious materials. I've been throwing that term out a lot, cementitious materials, and you're thinking, well, isn't that just cement? Well, for the most part, yeah, it is cement, but there are also some other materials that we can throw into a mix that can act as a cementitious material and ultimately reduce the amount of cement that we throw into the concrete. See, cement can be expensive, okay? So if you can reduce the amount of cement but still get the same properties out of a given mix, we'll do so. You'll save some money. One very popular and probably arguably the most commonly used supplementary cementitious material is fly ash. Okay, have anybody ever heard of fly ash? It's a byproduct of the coal industry. We're in West Virginia, so it can be somewhat more available in this area. It'll increase your workability. It'll lower your heat of hydration. So if it's available and if it will work for your given application, it's definitely something you'll want to consider. Slag cement, which is what you'll get from a blast furnace, let's say at a steel mill or something like that. It can be used as a cementitious material. Silica fumes, any other natural pozzolans or whatnot can be used to ultimately reduce the amount of cement that goes into a given mix. Any questions? I feel like a lot of the content of this, a lot of this is really definition and terminology stuff, and like I said, my main goal is I want you all mixing, I want to get you all doing mix designs as soon as possible. So are there any other questions about this, about just basics on admixtures and Portland cement? Okay. I'm going to pull something up real quick, and I'm actually passing this out. Okay. So let me show you something. What I've done is this. So let's see, 1, 2, 3, 4, 5. This should be on MU Online right now. If not, let me know. It's on there? Okay, good. This is the popular row. I don't know what's going on here. There's so many people here. I'm going to give you all yours last. 1, 2, 4, 5, 6, 7. There you go. That was just mean. I'm going to correct that. All right. Okay. So while this is getting passed out, I want to show you what this is so that you all are aware of this. The proportioning of a concrete mix is a little bit of a lengthy process, and there's really no way to avoid that. It is what it is. Okay. What I've done in this handout is I've kind of summarized a lot of the data and tables and provisions that are in Chapter 7 of the book. Largely what we're going to do with proportioning concrete mixes is, first off, when possible and when available, you will definitely want to use any locally available data. I mean, like, for instance, your local aggregates are going to behave maybe a little differently than general aggregates, if you will, and so on and so forth. But what I'm going to do, or what I've done here, is I've essentially summarized each of those steps as well as snipped all the appropriate tabulated data in this particular handout. So a lot of this isn't going to make a lot of sense right now because it's just a bunch of tables and equations and you're like, what's going on? But let me explain what we're going to do. I'm going to sort of one by one go through the concrete mix design process. I'm going to explain, what we do, how we go about it, and that'll take today and probably a little bit of next time. On next Thursday, we are going to do a full-blown start to finish design example. Okay, and we have a couple examples in our lecture today, but they're really simple and really straightforward. But I believe, between now and the end of next week, you all will understand start to finish how to proportion a start to finish concrete mix, and that's sort of my my goal. So let me see. Okay. Oh, let me do this. We're going right on. Okay. Now, a couple things. So you're going to hear me just say concrete. Okay. We are specifically, and if I want to get specific, we are learning how to proportion Portland cement concrete, and by that I mean concrete with Portland cement. Remember last time we were talking about how cement, we're technically talking about Portland cement. Remember, it comes from the Isle of Portland. If you ever hear me term concrete, I am talking mostly about Portland cement concrete. In other words, Portland cement is the cementitious material. When you are looking at a given concrete application, typically what happens is one engineer will design the mix, and one engineer will be responsible for the final quality, sort of that QA/QC process. A few tidbits. We're going to use this quite a bit in our calculations. 1 cubic yard, if you've ever heard the term a yard of concrete, we're talking about a cubic yard. 1 cubic yard is 27 cubic feet, 3 times 3 times 3. So we'll actually need that conversion throughout our calculations. In terms of applications, normal weight concrete tends to weigh around 140 to 150 pounds per cubic foot. A very useful term, or a very accepted quantity when you don't know. Normal weight concrete tends to weigh around 145. That's what we use for a lot of structural applications. But if you're determining the weight of reinforced concrete elements, we usually don't use 145, we use 150. And the reason why is because you got normal weight concrete, but you got rebar in there. And rebar is made out of steel. Steel's heavier than concrete, so we bump it up a little bit. That's normal weight concrete. Lightweight concrete, if you're trying to shave some weight on, let's say, a given structural application, maybe you can do so by shaving the weight. Lightweight concrete tends to weigh around 110 to 115. Can be a little more expensive, but maybe it's necessary for your given application. Okay, now if you're trying to ensure a quality batch of concrete, it's really a function of two things, okay? And the final quality, all this matters, okay? But really the two big hurdles that you got to assess is, number one, design mix issues. And I've got this concrete lecture sort of split up into part one and part two. And part one is going to be the design mix issues. So the composition, the aggregates, the water, the admixtures, proportioning those components, all of that. The second big component, which is just as important, is proper handling and curing. You know, transportation, hydration, how the concrete is placed. Do you use vibration? And if so, do you do it properly? How do you cure a given concrete after placement? All this stuff matters, but we're going to sort of handle it one at a time. We're going to start off with design mix issues and then get into handling and curing later. So if you want to be successful at placing a given or doing a given placement of concrete, I do my best to try and avoid the term pouring concrete. We're engineers. We don't pour concrete. We place concrete. So no pour. I'll be honest. I do say it every now and then, but it's place. Place concrete. So if I said it before. So successful placement of concrete results from, you know, getting a lot of stuff right. You know, first thing we've got to do is we've got to get our mix design proportions right. If you're starting literally from scratch, you'll probably want to do some trial mixes and test those mixes to ensure that what you're producing is accurate. Now, a lot of you know, concrete ready mix plants and things like that, they've been doing this stuff for years. They've got their mix design process down pat. I mean, they're always doing regular QA, QC, so they're sort of doing this, you know, throughout their business operations. But once you've got that taken care of, get everything weighed and batched together, you know, get it all proportioned, then begin mixing. The clock starts, because once you get water in contact with that cementitious material, that's when the clock starts, and that's, you know, when that's when you have to start timing things out, getting ready for placement. So obviously you got to transport that to the site where the concrete's being placed. Usually during placement or right before placement, you're going to have to draw some samples to do things like slump tests, air content tests, cast some cylinders for 28-day testing, all of that. You've got to place the concrete. Once it's placed, you'll need to consolidate that. Now, I mean, you can work around that if you're using something like self-consolidating concrete. But if not, if you're using regular old concrete, you know, for instance, if you're casting a bridge deck, you'll cast that bridge deck. And if you've ever seen that construction process, you'll see these guys with these, construction workers, and they'll have these vibrators, and it's, you know, it looks like a long sort of metal shaft, and you stick that in, and it vibrates, and it gets the concrete to fill in all those, you know, given voids and spaces. And we've got to do that appropriately. Finish the surfaces, prepare it for curing, and then there you go. All right. Everybody good with that so far? So there's a rather step-by-step process that needs to be followed for successful placement of a given batch of concrete. Now, in regards to mix designs, we really need to try and, there's three qualities that we're really after. Okay, we want to have acceptable workability. I mean, we might have a mix that has all the necessary strength and it's the most economical design possible, but if it's not workable, it's not going to be placeable, and it's not going to matter anyways. Okay, so we need acceptable workability. We want to make sure that we're getting the hardened properties at the end that we're after. So we want, you know, acceptable strength, acceptable durability, so on and so forth. But it also has to be economical. So one of the sort of the key aspects of it being economical is that you want to use available materials, you know, locally available aggregate, so on and so forth. Okay. Now, what I'm going to do is I'm going to talk about some simplified mix design methods, you know, really simple, straightforward stuff. But the refined method that we talk about, that one's going to be a little lengthy. So first off, if you've ever mixed concrete you know, like for a project in your backyard or something like that, you might have heard of the 1, 2, 3 method. Anybody heard of that? If not, you either use that or you probably use like Quickcrete from Lowe's, right? Okay, all right. Well, one of the simplest means to mix concrete is to use the 1, 2, 3 method. And the 1, 2, 3 method is as follows. First off, it goes by volume, okay? So you're measuring volumes of given ingredients. And the 1, 2, 3, it's easy to remember, okay? 1 part cement, 2 parts sand, 3 parts gravel. That's it. And then once you've got those mixtures together, add enough water to get your desired workability, and there you go. Now, let me be clear. This in no way, shape, or form would be appropriate for a large-scale, force-resisting civil engineering structural application. This is just the patio in your backyard or something like that. But you at least can do a basic mix design. So maybe like 1 bucket of cement, 2 buckets of sand, 3 buckets of gravel, something like that. All right. Sound good? All right. The proportion method gives you some very conservative mix design proportions. It's a little more accurate. It's used for small jobs, but it's also a pretty simple, straightforward approach. And I call it the table method because you're literally just looking up your mix design proportions in a table. So first off, if you see me refer to any tables, table 7.11, 7.12, these are coming right out of your book. Okay. So to give you kind of an idea, this is table 711. Now this is relative components of concrete by weight. Okay. So for instance, based on your given aggregate size and whether or not you're dealing with air-entrained concrete or non-air-entrained concrete, what you're doing is you're looking up proportions of each of these aggregates by weight. Now, if you take any row of these numbers, like let's take this one right here. Okay, somebody got a calculator? You're engineers, you should have calculators. My goodness. All right. Add up these 4 numbers right here and tell me what you get. 1. All right. Everybody else get that? Okay. What's that? Everybody got 1? Okay. So basically what this is saying is that if I have non-air-entrained concrete and I know my nominal maximum aggregate size, right? We learned about that with aggregates a little while ago. Then if I've got 1.5 inch nominal maximum aggregate, I throw about 15% by weight cement, 28.7% by weight of sand, 50% gravel, and 6% water. That's it. Okay. Now again, these are simplified methods, but I do want you to be aware of them. This is a similar one, but this is by volume. So instead of measuring by weight, you're saying, well, how many buckets do I need by volume? So just to make sure everybody's aware of this, if I wanted to use, let's say, the proportion method to design a batch of 4,000 pounds of non-air-entrained concrete, okay, so 4,000 pounds of non-air-entrained concrete, right? And I'm doing it with a coarse aggregate that has a maximum aggregate size of 3/4 of an inch. It's pretty straightforward, okay? So this is by weight because we're looking for 4,000 pounds, okay? So I'm looking by weight. It's non-air-entrained, and I had a maximum aggregate size of 3/4 of an inch. So I'm literally looking at these numbers here. Make sense? Everybody okay with that? So non-air-entrained concrete, 3/4 inch nominal maximum aggregate size. Here's my proportions. So 0.17, 0.32, 0.442, and 0.068. Okay? So if I was proportioning this mix, I'd say, all right, we'll start off with the cement. And to determine the weight of the cement, all you do is you say, all right, 4,000 pounds times that proportion, which was 0.170. And what does that come out to be? $680 pounds. Do I have a second on that? All right. So that's cement, and then you just go down the line. So we'll say sand. And by the way, you might hear me interchange the terms sand and fine aggregate or gravel and coarse aggregate. I'm probably going to interchange those a little bit. So 4,000 pounds times, and that index was 0.32. What does that come out to be? 1280. All right. So gravel, that was 4,000 pounds times, what was that? I think it was 0.442. And that is what? 1768. Second on that? All right. And then water. 4,000 pounds times, I think that's 0.068. Okay. What you are seeing right there, that is what I mean by when I say a mixed design. That is a mixed design. In other words, a proportion of, for a given quantity of concrete, how much cement do I throw into it? How much water do I throw into it? How much coarse and fine aggregate I throw into it? That is what I mean by when I say a mixed design. Okay? Yes? Well, that, okay, this is a really good point. Okay? Two things. One, let me say this. Okay, one, you are right. Okay? And just to get, nitpicky on the next example proportions by volume. Okay? But in our refined methodology, okay, which is what I'm going to talk about later, okay, we actually have the option of proportioning by weight and proportioning by volume. And what we're going to do is proportion by volume. And so let me explain how it's going to work. Okay, so and I do want to delve into this a little bit because it's a really important point. So four main ingredients: cement, water, gravel, and sand, right? Okay. So this is how this is going to work. So we use our three key pieces of information at the very beginning: our target compressive strength, our data about our aggregates, and our intended use, right? Now, what we're going to do is this. We're going to use that data to sort of determine how much cement needs to go into it, how much water needs to go into it, and how much coarse aggregate needs to go into it. And we're going to use those three, and then we're going to back calculate how much fine aggregate needs to go into it. There's no real reason why we're back calculating that one. It's just the way our procedure goes. We tend to go with water and cement first because those are our cementitious, that's where a chemical reaction comes from, and most of our strength comes from coarse aggregate. Now, the way that we determine the amount of fine aggregate is not from a weight proportion method, it's from a volume proportion method. So what we'll do is this. We'll say, all right, we know how much water, cement, and sand needs to go into it, right? We'll take each of those quantities, determine how much volume that takes up. Then we'll say, okay, how much additional sand will need to go in there to get 1 cubic yard. Make sense? Be clear, these are really simple methods, though. But you are exactly right, though. The only other thing I would add, and that we're really not talking about, is waste factors. Okay? So what I mean by that is, and this is a really simple concept, but it is something worth mentioning. If you need to if you've got a given project and you need to place 10 yards of concrete, do you order 10 yards of concrete? No. You order a little bit more to account for spillage, and it's called waste factors, okay? So if you wanted to apply, let's say, a 10% waste factor, and you needed 10 cubic yards, order 11 cubic yards. Order a little bit more, okay? Everybody okay with that? Just something to keep in mind. I'm not going to do example 8b because it's literally the exact same example, just using a different table. If you understand how to use this, then you understand how to use this. You all can do that on your own, and I've got the answer, so if you want to follow along with that, you're more than welcome to. Okay. Everybody good so far? Okay, let me see what time it is. Oh, we're doing good. We're doing good. Okay. All right. Those are simplified methods. Here's your refined method. This is what's being talked about in this handout. Okay? I'm going to take this I don't want to say take it really, really slowly, but I really want everybody to understand what we're doing and why we're doing it, okay? So, like I said, we're going to take our 3 fundamental pieces of information, intended use, data about our aggregates, and our target compressive strength to proportion our mix, okay? Here are our steps, and we'll take them one at a time and make sure everybody understands what's going on, okay? So let's take it slowly because we got plenty of time. Okay, so step 1 is to determine our required compressive strength. Now, a few of you have already had me for reinforced concrete design. I hope that a couple of you elect to take it next semester. The guy who's teaching it, I know he's a jerk, I know, but it's a joke. But in reinforced concrete design, you know, for those of you who aren't sure whether or not you want to take it, in reinforced concrete design, what we do is we take the principles that we learn in structural analysis, and we then look at the flip side of the equation. We say, well, how deep does that beam need to be? How many pieces of rebar do need to go in that section in order to safely resist those loads? And that is the primary purpose of reinforced concrete design. And we'll look at beam design and slab design and column design and the like, and that's what we're focused on, is looking at proportions of reinforced concrete elements. And if you've had that class, one of the things that you'll remember is that one of the very first values that we assume about a given concrete, or about a given concrete design problem, is we assume FC prime, okay? Now, FC prime is the compressive strength of a given batch of concrete. So what I mean by that is, you know, we're going to go into the lab and we're going to bust some cubes, right? So what we're going to do is we're going to take a cube, we'll go like this, and we're going to compress it, and go till boom, till it fails, okay? Now, it's going to have some load, you know, make up some number. Let's say it's 10,000 pounds until it fails, okay? So 10,000 pounds is going to be the load. Well, it's a cube that has an area 2 by 2, right? So 4 square inches. So if I take 10,000 pounds, divide it by 4, what is that? 2,500. And what are the units? PSI. I propose that for that batch of concrete, its compressive strength is 2,500 PSI, okay? The amount of pressure, the amount of stress that it would take to fail that given element. Make sense? Okay. So at the very beginning of a given mix design problem, that is a quantity we are going to know, because the structural engineer or geotechnical engineer, what have you, when they performed their design, they assumed an initial compressive strength. So we're going to be given that compressive strength, and that's going to be a target for our design. Make sense? Okay. Now, you should know as well enough by now to know, okay, let's say I mix up some concrete and I test a bunch of cylinders. Let's say I test 10 cylinders. Do you think each one of those cylinders is going to have the exact same compressive strength? Of course not. There's going to be some scatter to it, right? Okay. Now I'm bringing up statistics, right? Is that another acute onset of post-traumatic stress disorder? Okay. You all remember this from statistics, right? The bell curve, normal distribution. If we assume a normal distribution of scatter of cylinder test data, okay, ACI, which is the American Concrete Institute, they specify a lot of the provisions that we use for structural applications in concrete. They define that the allowable risk is a 10% chance that the compressive strength of a given mix is less than what's specified. So what that means is this. If the engineer comes to us and they say, I got some concrete that I need you to mix for a beam design that I did. And when I did that beam design, I designed it for a compressive strength of 4 KSI, 4,000 PSI. When we design our mix, we are not going to use 4,000 PSI. We are going to bump it up some. We are going to bump it up such that there is a 10% chance that the compressive strength is lower. Now, how do I get that 10% chance? I go to the bell curve. For those of you that have had statistics, do you remember Z-scores? Remember that? Okay, if you look up the Z-score such that the area under a normal distribution is 10%, that risk is 10%, you will find that Z-score is 1.34, okay? In other words, 1.34 standard deviations away from the mean, okay? So this is what the engineer specifies FC prime What we're actually going to use is FCR, a required compressive strength for our mix. Everybody okay with that? Okay. Now, we put a little bit of a caveat on that, and we say if you go through and do a bunch of testing, let's say you do a bunch of testing, and you have a really, really large standard deviation, what that means is that your tests have a lot of scatter. And because you have a lot of scatter, we're going to throw a little bit more of a stringent requirement on you. So that's where this equation comes from. Okay, so step one says to compute a required compressive strength. And if you got a tolerable, regular standard deviation, we take our compressive strength and we add 1.34 times the standard deviation. Okay, that's if we have what I'll call a regular or low standard deviation. And by that I mean any standard deviation that's less than 500. Okay, if you got a really large standard deviation, we're going to throw a little bit more of a stringent requirement on you, and we're going to make you compute your standard deviation using the following relationship. So that second equation is just if you got a really large standard deviation. Everybody with me so far? Now, this relationship assumes that your data follows the bell curve, right? How many tests do you think is enough to know whether or not your data follows the bell curve? 2? 3? I say not, okay? And neither does ACI, okay? This equation assumes, if we're following the bell curve, this equation assumes that you've got at least 30 samples that are tested for a given concrete batch, which is not that unheard of if we're talking about large concrete mix plants. I mean, just look at here. Each group in this room, each of the 6 groups, each group is going to cast 9 cylinders. So we're going to have 54 cylinders for this class. So it's not that unheard of, okay? Not that bad, all right? So we're going to assume that 30 samples are tested. If you've got less samples that are going to be tested for a given mix, then we say, oh, well, if that's the case, we're going to have to bump up that required FC prime. If you're going to perform less testing, we are going to place a more stringent requirement on your resulting mix design. Does that make sense? Everybody okay with that? All right, so if you've got a standard deviation from anywhere from 15 to 30 samples, what we do is we take that initial equation and we adjust it by a modification factor. And what you'll find is the fewer and fewer tests that we perform, the more or the higher the required compressive strength will be. Now, I'm sure somebody's going to ask, well, this is if you're doing 15 tests, this is if you're doing 20 tests, what if you do 16 or 17? Just linearly interpolate, okay? Does that make sense? Everybody okay with linear interpolation, I hope? What's that? By now you should be. I know you are. From all the stuff we did in concrete design and steel, you should be good. Well, don't have that look on your face like, oh, God. All right. So if you've got, so if you've got 15 to 30 samples, you are going to adjust your model a little bit. If you aren't testing hardly any samples at all, then you're just going to use the following table. Now, one thing I will point out, if you look in your text, you're going to see quantities, and then you're going to see equations or quantities that are in parentheses right next to it. Okay? So this is the metric term. This is the U.S. units term. Okay? So this would be in megapascals. This would be in PSI. Everybody okay with that? So far, so good? All right. Okay. So step one was to determine what we've got to design for. Okay? And again, that is always going to be higher than what is specified. The engineer might come in and say, I need a 5,000 PSI batch of concrete. Our design might be 6,200. Okay? Because we have to account for that scatter, and we have to account for that acceptable risk. Make sense? Now, once we've got our required compressive strength, we can go to work. And the very first value, the very first quantity that we will determine is the water-cement ratio. Now, what we're going to do is this, and typically water-cement ratios rely on historical records. Now, we're in a classroom setting, we're in an academic setting, we don't have any historical records. So we're just going to go off the historical records that are presented in the textbook. But if you are completely starting from scratch, make a few different trial mixes at different water-cement ratios, do one at 40, 50, and 60, test them, and plot your results. And then now you've got some trends that you can build off of. And then you can keep building off of them more and more and more with more data. So if you go to Table 7.1 in your textbook, now the Table 7.1 can be used in lieu of experimental data. Okay? Now, anybody who opens their textbook, they're going to see Table 7.2, and they're going to go, well, what's going on with Table 7.2? I'm going to get to that here in a second. Okay. So Table 7.1. Typical relationship between water-cement ratio and compressive strength of concrete. So, based on a given FCR, required compressive strength for our mix, okay, so based on a given value, whether or not we're dealing with non-air-entrained concrete or air-entrained concrete, we can determine what our required water-cement ratio is. Now, what happens if your required compressive strength is 4,200? Linearly interpolate. Okay? Everybody okay with that? Now you're going to see Table 7.2, and it's going to look very similar. You're going to say, well, why aren't we using that? Okay? Table 7.2 is used for smaller, non-critical applications. I'm going to assume that the mixes that you are going to be designing as civil engineers are going to be critical. So we're going to go off of our civil engineering critical application ratios. Everybody okay with that? Okay, now, one of the things that you will need to do when determining your water-cement ratio is you're going to need to check that water-cement ratio against maximums, okay? Again, let's be clear. The more water you throw into a mix, the weaker it's going to be. So it makes sense that there are some limits placed against how much water that you can put into a given mix, and that's where we measure that by water-cement ratio, obviously. So if you look at Table 7.3, okay, so Table 7.3 will list maximum water-cement ratios and minimum design strengths for various exposure conditions. So let's just take a look at this. So if I look here, I say, all right, let's look at the second one. So concrete intended to have a low permeability when exposed to water. Concrete exposed to freezing and thawing in a moist condition or de-icers. Reinforced concrete exposed to chlorides from de-icing salts, salt water, brackish water, seawater, or spray from these sources. So to give you kind of an idea, this last one, this would be, let's say, a bridge pier out in Miami, okay? That's going to be, let's say, in the water. That's going to be subjected to seawater and brackish water and things like that. So our maximum water-cement ratio for that application would be, let's say, 0.4. But if we were looking at, let's say, a bridge deck in West Virginia, that's going to be subjected to freeze-thaw. Obviously, throughout the year, that's very possible given our weather conditions. And it's going to be exposed to potential de-icing chemicals like road salt and whatnot. Then that's going to lead to a maximum water-cement ratio of 0.45. So you might compute something from this table, and that table is essentially coming from this. You might compute something, but then you also might be limited to what's going on here. Excuse me. Another requirement that is going to be on your water-cement ratio is going to be based off of sulfate exposure, whether or not that sulfate is going to be present in water or it's going to be present in a given soil. So, soil mechanics, you all learn how to assess that. But whether or not you're going to have negligible, moderate, severe, or very severe exposure, your water-cement ratio is going to be limited accordingly. Everybody okay with this so far? Very good. Okay. Now on a side note, and if I hear about this, I'm going to say, come here. I'm going to have you stick your hand out, and we'll do that. Okay? All right? Don't ever let anybody add water at the job site. Don't do it. Okay? Don't do it. Don't do it. Here's why. Okay? What's that? Don't let them add water at the job site. Don't do it. Well, let me explain. All right, yeah, they do. Now you're engineers. Let me explain what happens. Okay, let's say you've got air and train concrete, and you've got, the mix design called for this much water and this much cement, and that's a water-cement ratio of 0.43, okay? 0.43 will tell you what your compressive strength is. If you just add a little bit of water, let's just throw about 10 gallons of water. Now, it'll be all right. It'll be all right. Go back and compute your water-cement ratio and look at your compressive strength. That can reduce your compressive strength by over 25%, okay? Now, for those of you that have had concrete design, reinforced concrete design, that's a big deal, isn't it? Right? Everything that you do in regards to safely sizing a beam, that beam might be supporting a bridge that your grandma's going to drive over every day. And they say, let's just add some water to the mix. Well, that bridge may fail, and grandma might be in the river. I'm just saying. So. What's that? Whoa. Whoa. That was Darwinism at its finest. So in Engineering 452, we're going to talk about ethical responsibilities of engineers. And the first and primary duty of an engineer is to ensure the safety and welfare of the public. Oh, my goodness. Okay. I'll mention this and then we'll call it, because I really do want to take my time with this process. Oh, it is. I know. We are going to go through it step by step. I know. Don't worry. Okay. So we've determined our required compressive strength, and we've determined our water-cement ratio. Okay? All right. So. Okay. The next thing that we have to do is we're going to start taking our ingredients one at a time and start determining appropriate weights. And so the first thing that we deal with is we determine the weight of the gravel, the coarse aggregate. Okay? We like throwing in a lot of coarse aggregate because coarse aggregate is really where we get our compressive strength. So more coarse aggregate, the better. Okay? But before we start computing weights, we need to compute. We need to do some checks. Now, I know we've said that when we look at a concrete application, we are working to achieve a target volume, which we will do. We will use volumetric methods later to ensure that our design yields, in fact, 1 cubic yard. That's going to be our standard. But in terms of measuring out how much ingredients go into a given mix, it's easier to measure by weight. So that's why concrete mix proportions tend to be reported in weight to achieve a target volume. Now, before we start determining the weights of coarse aggregates, we kind of have to do this anyways, but since we're talking about gravel, this is a really good place to do it. We need to determine whether or not the gravel that we are using is going to be appropriate for a given application. Now, what I mean by that is this. So when you do reinforced concrete design, one of the key aspects that you have to assess for a given design is what are called cover requirements. Okay? And cover is essentially the space between the edge of your, let's say, column or beam, or the formwork, if you want to look at that, between the edge of the formwork and the edge of your rebar. Okay? And different applications are going to have different cover requirements. Like going back to my example about the bridge pier in Miami. The bridge pier in Miami might have cover somewhere between 4 and 6 inches because metal corrodes, right? So we want to encase that rebar inside that element a little further than if we were looking at, say, a column in this building that is completely shielded. It might only have cover of 1.5 inches. So think about that. There's only 1.5 inches between the surface of that rebar and the edge of the column, right? Now, what if your maximum particle size for your coarse aggregate was 3 inches? Would that be an appropriate aggregate for that application? No, right? So your aggregate size has to be comparable to the application. Okay? Now, this note here is kind of important. This step 3, this is the only point in the design where the maximum aggregate size is used, right? Remember, there's a difference between nominal maximum aggregate size and maximum aggregate size, right? Nominal maximum aggregate size is if you look at your sieve analysis and go from the top and work your way down, Nominal maximum aggregate size is the first one that retains any aggregate. Maximum aggregate size is one more. And for this application, we're going one more because we want to be conservative in ensuring that we're using the right aggregate for the right application. Make sense? Everybody okay with that? Okay. Now, I'm sure I put this on here for a particular reason. Now you know what the standard sieves are. So if you do your sieve analysis and the 1-inch sieve is the first one going down that retains aggregate, this is your nominal maximum aggregate size. That's your maximum aggregate size. It's the 1.5. Make sense? Everybody okay with that? So what we would do is, based on that aggregate size, we'd say, all right, if we're looking at form dimensions, our max aggregate has to be less than or equal to 1/5 of the minimum clear distance. So that's between your forms. If we're looking at space between between individual pieces of rebar, 3/4 of that distance. Clear space between the rebar and the form, 3/4 of that space, and so on and so forth. Does that make sense? Everybody okay with that? All right. To be continued. All right. This is what I'm going to do. I'm going to stop this right here. Okay. And next time, this is what we're going to do next time. Next time, I'm going to finish this explanation process. And the next Thursday, we're going to use this handout, start to finish. We're going to design a batch of concrete. Sound good? All right. We'll meet back up at 2 o'clock.